Hello students. Now in this section we will try to find out moment of inertia of some continuous masses which are not like point masses, they are continuous masses distributed around certain axis of rotation, and what would be the moment of inertia. So one of the simplest thing would be to take a thin rod. Now when I say thin rod, what is it? What does thin mean? A thin may be a very fat rod for a say an ant or so. So what is a thin rod? If the width, if the cross section is way small compared to the length of the rod, so that's a thin rod for you. So I'll draw some width to that. Mind you, when we are become a little pro in this, we'll be doing moment of inertia, finding the moment of inertia of rods which are not so thin and whose cross section is comparable to the length, and then what all things we'll have to take care of that time, we'll find that. So suppose I want to find the moment of inertia of a rod which is having a length of a mass of m and a length of L. The total length is L of the rod, and the moment of inertia I am trying to find about the axis which is passing through the center of the rod, and it is uniformly distributed mass. Center of mass lies over here. So I can call the moment of inertia which I am going to find as ICM, moment of inertia about the center of mass. Now how to do that? It's the same thing what we were doing earlier. We have to find the moment of inertia of each and every particle which makes the rod and then add up all the moment of inertias. So I'll take a very small particle over here, suppose. Mind you, I can't take a fat particle, I can't take the width high, because if I take a high width particle, then the distance of the particle from the center cannot be assumed to be the distance of the center of mass of that particle to the center. This is what we have discussed in the earlier section. We can't just claim that the whole of the mass lies at the center of mass, then we go wrong in rotation. So that is that's the reason why we can't simply take a particle having a considerable width. Otherwise we could have taken the whole rod. In fact, the whole rod, this much of the rod, and the mass is at the center. If you assume that, then the moment of inertia is 0. So furthering that logic, if I take this much of the rod and say the mass, that much of mass lies here at the center of that, and then moment of inertia of that particle would be mass of that much into this distance square, that would be wrong, because again we are doing the mistake of taking the whole mass at the center of mass of something. So how small can we go? We have to go very small, such that the mass can be considered as a point body. So thank God we have calculus developed for us in maths. We have calculus which can be applied in physics over here. So where this width, even though I am showing it as a big width over here, but you would know that this width, let me call it as dx, is so small that it can be considered as a point body. So what we can consider is that this rod, instead of being continuous, it is like those widths, it is at the center of these small widths are small masses. Those masses I'll call it as dm. Dm exists right in the middle of this small width, and like these small dots, it is as the case it was when I was doing the previous section. Small dots all over, which could be some 5-10 dots are there which would be counted. Here it will be numerous dots, but the method will be same. So we have assumed it to be dot, but the dots are so close that they are in the span of dx, and that is how we proceed to find the moment of inertia. So it is very well proven that calculus actually works. So I mean, if you try to calculate the area of a triangle or area of a rectangle, say area of a triangle through calculus, then it gives you the same area as half the rectangle, which is half into base into height. So in calculus you will be putting discrete steps, but steps are so small that it can be assumed that this is going very smoothly, very smoothly, and gives you the perfectly correct answer of had it been absolutely smooth. So calculus does work. So we are going to employ calculus over here and try to find out the moment of inertia of that small mass, and then since we have taken that small mass at a random place, That's the essence of integration. You have to take it at a random place, not at the starting of where you think, not at the end of where you think your calculation is, but at a random place, and do the integration, put the correct limits from the starting point to the end point, and you'll get the answer. So before going on to do the integration, I'll just again emphasize that what we have to do is, we have to, step number one is to choose the correct dm, a small piece of mass which can be represented as a point mass, or it can be a set of masses, not necessarily point, but the distance from the axis has to be consistent, has to be same. So we have to choose a dm correctly. So here the choice of dm is this, and we'll do some other questions where we'll have our comfort level will increase over there of choosing the dm correctly. So once you have chosen the dm correctly, and then you have to specify the distance. Yeah, there has to be a variable how far the dm is from the axis of rotation. So in this case, say x is the distance. These two variables are very, very important for you, because ultimately the small moment of inertia of that thing would be equal to, now since it is dm, I'll call it as di, small moment of inertia, is equal to that mass, which is dm, into the distance square. So x square, I'll just write it over here, that is x square dm. That's your di. So writing this much is the key. It is the first step and the most important step. So if you get this right, then you are halfway through the thing. And then the next one is, x is a variable, dm is a certain width, what you have taken, a very, very tiny width. You have to connect the dm variable with the x variable and have it in a single variable, so that you can integrate. That single variable can be a theta, maybe m, maybe x, whatever, but it can't, if you just integrate like this, we can't integrate two variables. We can't integrate x squared dy unless until we know the relation between x and y, so that we can present it as a single variable. So this is what we can integrate. So where your x has to be written in terms of y, or vice versa. So now coming back to this, what I was saying is your dm has to be related. Now how do you take your dm? Since the variable you have taken, which is a variable of the distance, which depicts the distance of the particle from the axis as x, you will go a little more than x to choose your next mass, and a little more than x, that little more is called dx. So you'll go dx further, so that your integrator appends by dx and forms the new x. So x plus dx becomes the new x and takes the next dx to go a little further. So that's the concept of integration. So your dx will be what dm is, because the next step is going to be dx away. So whatever is between your x and x plus dx, that much should amount for dm. Again, this is a very, very simple thing what I'm saying. It is almost evident, but you should always put some thought on this before hurriedly going on to do the integration, because at times there may be a catch over here. There might be some catch over here. Okay, so here there is no catch, so we'll continue with our process. So dm is having the width of dx. So how do we get the value of dm? Quite simple. A hole of length L was having m mass that was given to you. So your dx length will have how much mass? Dx length will have m by L times dx mass. Simple unitary method. So you can say mass per unit length was m by L, and the length of dx will contain so much of mass. So that's your dm. So we'll quickly go on to write the dm value over here. So that gives me m by L and dx. So that's your di. So that's the moment of inertia of this small part. So similarly, the moment of inertia of all small parts on this will have a similar format. The format is not going to change. It's the x variable if I take somewhere else, and the dx. Hence, we can safely integrate it. So once we integrate this on both sides, what we get here is the moment of inertia. Here we have to carefully choose our limits. Like if you have to do the integration of the whole of the rod, what's the moment of inertia of the whole of the rod? The x starts from your minus L by 2 and goes on to plus L by 2. So the whole length was L. So from here is what you are taking your x. So this side is minus x by 2 and sorry, minus L by 2, and that side is plus L by 2. So minus L by 2 plus L by 2, your m by L being a constant goes outside, x square dot dx, and what you get is m by L x cube by 3, and obviously the limits minus L by 2 to L by 2. So you replace your x with L by 2 and a minus L by 2 and do a subtraction of them, and what you get is m by L by 2 whole cube minus of minus L by 2 whole cube. So that minus of minus, the cube gives retains the minus, so it becomes a plus. So you get a L cube divided by 8 over there, and the 3 was already there. So I'll just put the 3 outside over here, or for the time being I'll just write over here, so that you can relate it straight away. And so you'll get a L cube, and one of the L gets cancelled, so it remains as L square. That's the correct unit for moment of inertia, mass and distance square. So ml square, and then you have a 1 by 8 plus 1 by 8, that leaves you with 1 by 4 times 3, so 1 by 12. So ml square by 12, 1 by 12 ml square is your moment of inertia about the center of mass. So this is, you'll be coming across this term so many times that you don't have to memorize it right now, and whether you like it or not, you will be knowing it anyhow. And suppose I say that I wanted, the rod was not rotating about the CM, that's your CM, but the rod was rotating about this axis. Many a times it is hinged at one of the ends. It can be hinged over here, it can be hinged over anywhere else. So how will you do? You will have to do the integration again, unless until you know there is another method which is called parallel axis theorem, which you can apply. So right now we have not discussed that. So I'll say that I'll do the integration again, and in that case again the distance you'll have to take from this axis. So you'll call this as your x, and that's your dm in a span of dx. So again the mass per unit length is same, so you will have everything in the same format till here, till this point, where you have to improve on your limits. So your limits would be x goes from 0 to L. So that would be from 0 to L. So I'll just write in green. When you are doing from 0 to L, you have your m by L outside, and you have x squared dot dx. So that gives you the moment of inertia about this point. So that was the one in, this one was in black, ICM through this, and then in green I'm doing I about one of the end axis. So what shall I write? About whatever, about the end axis, about one of the end, okay, about the end axis. So this is what we'll get when we are doing I about the end axis. So this is for this. So what we have is x cube by 3, and when we replace with the limit, it will be L cube by 3 minus 0 cube by 3. So that's L cube by 3. So what we'll have is ml square, because one of the L's will cancel and the 3 remains. So that would be the answer for one of the ends. So like this, you can have the axis from anywhere, and then unfortunately, if you don't know parallel axis theorem and all, you'll have to integrate all the time, again and again. But fortunately we have a theorem for that. So we do the integration for one of the axis, and then we can find out for the other axis. The preferred axis of doing is always through the CM, and then transforming to any other axis becomes a easy job. Now go on to say something, and we'll not do the calculation. We'll just go on to just tweak the question a bit, improve the question a bit, and see whether it changes my answer or not. Suppose the rod was not a thin rod, and it was having a decent cross section area, and again I want to find mass is again m, length of the rod is L, and I want to find the I about the CM. Again it's going from the center of mass like this. Will it be ml square by 12 I is equal to ml square. Okay, capital M I have written, so capital M L square by 12. Will it be that? Not at all. Not at all. Where's my red pen? Not at all. Now reason being, why not? Why it is not that? Now let me just say that if I have taken a dm over here having a width of dx, so it will come like a disk. It will come like a disk, and that's your dm, which is coming like a disk. That's your dm. Now, do you think that each and every part of that disk, which is, it's not a point thing. So if I take this integration as my basis, this integration as my basis, then what was the x? X was the distance of the axis of rotation from the mass. So the axis of rotation from the mass is not always same. The one which is outside, the part of the mass which is outside, the distance of that from the axis of rotation is something else, and the part which is in line, like this diameter, I still agree all the masses on this diameter is having the same distance, xxx, but the ones which are outside the diameter and which is inside is not having the distance x. So we are doing the folly of presuming that the disk has all the mass at its center, or at least the central line. So it is having all the mass at the center, and that dm presumed to be at the center of this disk is x away, truly, but that presumption that all the mass, a distributed mass, lies at the cm of that is the basis which is absolutely wrong in rotation, and hence we have this moment of inertia as a topic, so which makes us more careful into dealing with the questions and studying the mass. So this was for a rod. I'll just quickly do one or two more and then pose your question with, say, a cone. Now suppose I say I have to find the moment of inertia of a ring. When they say ring, they generally mean that the width is very small. There is no width to it. Otherwise, they will mention the inner radius and the outer radius. If just one radius is mentioned and it is called a ring, then we assume that the thickness is very small compared to the total radius. So your, say, mass is m and radius is r, and the axis is this going in and out. Okay, so what is the moment of inertia of the ring? I'll say that asking this is as good as asking, this is surely a continuous body, so I'll compare it with a continuous body. So that's a rod, a very thin rod. Again, the width is very thin compared to the length. It is again having a mass of m and length of l, and it is, say, say it is d away. This radius was r, that's d away, this radius was r. Okay, so it is a continuous body. So what do we integrate to get our answer? What do we integrate? Now our integration means using things very, analyzing things, getting the i's very carefully and integrating all the small di's, right? So getting the di's, so you'll have to take a small mass. Say I took a mass over here and call it as dm. The distance is d from the axis of rotation. I take the next mass and the next mass and the next mass. So taking it from the up, I can call this distance as x and these distances as dx, the small one, and the next one, and the next one, and the next one. Your dm is, again, as I said earlier, your dm is m by l dx. And what's the distance of all of them, all these dm's from the axis? The distance of all the dm's from the axis is d again. It is d only, it's not changing. So your di's are your d square, that's the distance, all the dm's into the dm. D square dm, this d is the distance, mind you, and that dm is the calculus dm, the small mass dm. So here if I'm trying to integrate this, if I want to integrate this, I see that d is a distance which is a constant, so the integration comes over here and d square being a constant goes outside. So do I need to replace the dm with the m by l dx and do it further, x going from 0 to l? I don't have to. Dm simply means the essence is all the small dm's added. Dm integration means all the dm's added. So dm added, dm, all the dm's added is going to give you the big M, the whole of M. So in this case, there was no need to go into integration because the whole of mass, all the mass lied at a distance d away. So I could have safely said that your I is equal to m into d square, because all of them, I take a big chunk, I take a small chunk or whatever, all these masses are having a moment of inertia of that mass into d square, that mass into d square, all added, which is the algebraic addition. The d square gets common and the mass gets added. So if the rod was like this as the earlier case, or say at an angle, becomes a good question, then all your dm's are at variable distances, then you rather do the integration. You won't be able to do it like this. So just by the basic definition, I mean, you'll have to go further and do the integration to get the answer. So over here again, why I equated this to this kind of question, why equated the ring to that kind of question? Because now we know the tool of integration and how to apply it. We should not be jumping and applying that tool unless until it is required. So here, if we had broken into small dm's with all our fancy variables, say at the d theta, the width is, it subtends the angle of d theta over here, and we get the length as r d theta. We can do all those stuff, but the point is that dm, all of them lie at the same distance r away from the axis of rotation, if the axis is like this, so no need of integration, and we can safely say that your di's, all the di's would be r squared dm, where r is a constant. All the dm's are having the same radius r, so r squared dm, r is a constant. If I integrate and get my I, then what we have is your dm gets integrated, r square dm gets integrated, which is nothing but the whole mass m. So you get a mr square if the axis was like this. So what I'm saying is, if the axis was like this, again and again I'm saying that, because had there been a ring and the axis was like this, it is along a diameter and that's your axis. You find your moment of inertia from an axis, not from a point. You don't find it from the center, you find from the axis passing through the center. So if in this case, if I take the dm's, various dm's having the same, I mean, it has to follow the same logic so that we can integrate. So all the dm's are having the same width. In this case of d theta, we can define the variables. So what we have is, all the dm's are at variable distances. The dm's, this dm is r away, but all of them are not r away. Some are very close, some are on the axis. Some means only two pieces will be on the axis, the rest are distributed along, and hence your answer is not going to be mr square. Will it be more than mr square or less than mr square? Quickly. Yeah, I think you guessed it right. The answer would be less than mr square. Answer would be less than mr square because it would have been mr square if all the masses were at r distance, but only two pieces, exactly two pieces are at r distance and the rest are closer. So it is somewhere in between. So you have to integrate and get the in between thing. It is not like half of r and then the square of that, which becomes mr square by 4. It is not necessarily that. It is not that, in fact, in this case. So how do you get it? You do actual integration. So I'll not do the integration. I'll ask you to do the integration and verify the answer. I'll help you in, since I made the diagram, I'll help you in creating the variables. So I might as well do the integration since it is just the second one. So I've just messed up the diagram this side, so I'll do it that side, and obviously we can integrate all over. So one is choosing the dm, choosing the distance of the dm in variables which will help you relate the distance and the dm in a single variable such that you can integrate. So I would propose more often than not, in the things which is involving a circle and all, use your variable as theta. Use your variable as theta. It is not necessary, and you can go for your own variable of your liking. I will take it as theta. Like the mass was x away from a certain point, the distance of the mass was x, and we had a dx going for going further from there. I'll take theta and I'll go a d theta further from here, so I'll make a big d theta. Obviously that d theta is a very tiny thing, but to depict over here I've taken a good enough width. So that's your d theta angle. So this mass which is within that scope of d theta, that span of d theta, I'll call that mass as dm. Between here to there, that's your dm, because the integrator I'm planning to have the steps in integration, the incrementing it does, I'm planning to have the steps of d theta on theta. So my main variable has to be theta and the steps is d theta. So when the integrator goes on to integrate the next stuff, it is d theta away. So you have rather taken care of all the things lying within that d theta scope, so that in the next step, which would be the next d theta, it takes the rest of the other mass. So you are not leaving up any mass, you are not overlapping masses. So there you have to be careful in integration, should not be overlapping, should not be leaving spaces. So that's my plan of integrating. And then the basic, how much is the mass and what's the distance from the axis. So I'll put it in black over here. That's the distance from the axis and that's the mass. So what would I write? I would write my di, I for that small thing, di to be the mass dm and into multiplied with the square of the distance of the mass from there. So what do you think is the distance? You can call it as x, but ultimately you'll have to, you can call it as x square, but ultimately you'll have to write everything in single variable, m also, x also in a single variable, so that you can integrate. So what do you think your x is? What's your x? What's the distance of the mass from there? So r is the radius known and this is the angle theta. So that angle is 90 minus theta. D theta hardly is anything in front of theta. This angle is, this dot angle is 90 minus theta. So how much is that? X is r cos 90 minus, r sin 90 minus theta. So that becomes r cos theta. Or you can have a look over here. That x would be this much, which is r cos theta. That distance is r, this angle is theta. That's a 90-degree triangle. So that's r cos theta. So what we have is r cos theta whole square times dm. Now dm also has to be replaced in terms of theta. So again, using the mass per unit length stuff, so we have dm is equal to mass per unit length, total mass divided by total length. 2 pi r is the total length times the length of this is r d theta. You could have also said that mass divided by the total angle, which is 2 pi into that much of angle, that is d theta, is the mass of that part. So m by 2 pi d theta. Here also you get the same stuff, there also you get the same thing. So dm, I'll replace it with m by 2 pi d theta. So what we have is, we have a bunch of constants like m and r square and 2 pi, which goes out of the integration, and you have a cos square theta d theta. That's your di. The rest is integration. So this is the bulk what has to be done, and I'm pretty sure by class 12 everybody will be doing integration like a piece of cake. It would be, I mean, these kind of integration will be very easy for you. So integration is not where I am concentrating on. Where my concentration is choosing the variables, fitting the variables correctly in what is required, and then integrating it. Now I hope you know that we don't have a formula for cos square theta, but we can change cos square theta to linear angles. So using what? Using cos 2 theta is equal to 2 cos square theta minus 1. So we have cos 2 theta plus 1 divided by 2. So instead of cos square theta, we can write mr square by 2 pi cos 2 theta divided by 2 plus 1 by 2 times d theta, and then we can go for the integration. So your I would be integration of this. Theta goes from where to where? From 0, take a whole round, so 0 to 2 pi. You can do an integration like that and get your answer. So you can do an integration from 0 to pi also, and the rest of it will be same, and you can say that this I of this thing and I of that thing will be same, so you can add the two and double it and get it. So try out all the fancy stuff. So I'm not integrating it right now, you can integrate yourself, or shall I? Okay, I'll do it. Okay, so what we have is, in fact, pause and integrate yourself, and then you check the answer with me. So what we have is mr square by 2 pi outside cos 2 theta d theta integration. So what we have is, we can put this cos 2 theta, half is there outside, cos 2 theta d theta. I can say d theta instead of d theta, d of 2 theta divided by 2. So I am doing that, d of 2 theta divided by 2. So we have this variable 2 theta and d of 2 theta matching, so that I can call it as sine 2 theta on integrating. So it becomes sine 2 theta, but I have a 2 outside and this 2 is also outside, so I get a 4 outside. For half and d theta integration, it is half, and d theta integration gives you theta from 0 to 2 pi. So further going on to that, sine of 2 theta, and you replace with the upper limit, which is 2 pi, gives you sine of 4 pi, which is 0, minus sine of 0, which gives you 0. So this part gives you 0. This part will give you 2 pi minus 0. So 2 pi by 2 gives you pi. So what we have is mr square divided by 2 pi times pi. So pi and pi gets cancelled, and yes, that's your answer. So your answer will be equal to, where shall I write it? I'll write it here. I hope it is in the screen. mr square by 2. This is I about a diametrical axis, dia. So you see, for the same ring, if the axis was this, you had mr square. About diametrical axis, it is mr square by 2. And fortunately, if we have learnt all the other theorems, particularly the perpendicular axis theorem, which we are going to do, then we didn't have to do this integration. It might look a little troublesome over here. We didn't have to do it, and our knowledge of perpendicular axis theorem would have given us the answer of mr square by 2 directly if we knew this mr square. So mind you, this is also ICM, this is also ICM, and that is also ICM, because both are going through the center of mass. So if they say that find the ICM of the ring, that's not a complete question. There are so many axes which can go like this axis, like this, not this. This we have already found. Whether this or this or this, all diameter will give you the same answer. But if there is a slant axis like this, slant axis, that is also going through a CM, so that is also ICM. So ICM was mr square if the axis was perpendicular outside, so perpendicular I'll write it, and ICM along the dia was mr square by 2. I'll remind you one more thing. As I told you earlier, ICM among all the moment of inertia of axes which are parallel to ICM, it is the least, meaning to say this ICM mr square is the least among all these axes which I make parallel, say like this axis or that axis or this axis. all parallel axes. This ICM mr square 2 will be least among all the axes which I make parallel to this. That ICM, a slant one going through the CM, will be least among all the axes which are parallel to that. So we'll come to that, the reason also. So I hope you got an idea of, even when masses are a continuous mass, there are a lot of it is made up of a lot of DMs which are all connected. Still, there might be cases like this rod lying along the axis and this ring. There might be cases where you don't actually require the integration and you can do it. But most of the other cases, for continuous masses, you will require to do the integration at least for one of the axes.